this extra practice video really covers everything about chapter 16-17, which is testing hypotheses about proportions or confidence intervals with proportions. So it's actually kind of putting it all together. So I suggest not only watching this the first time through when you're learning everything, but this is a really good refresher for right before you take your assessment, because it goes through everything really that we've talked about and make sure you understand it. Again, I want to go through one more full example with you that includes doing everything by hand, checking the conditions, and then verifying the results in StatCrunch. So let's say there are supposed to be 20% orange M&Ms. So again, what does that tell me? That I'm assuming that P is 0.2, 20%. Suppose a bag of 122 has only 21 orange M&Ms. Does this contradict the company's 20% claim? Check with a 95% interval. So again, this means that P hat is 21 out of 122, which we'll calculate in just a moment, and that I'm going to check it with a 95% interval. So let's first check the conditions. And again, this is just going to be given to us this week. The conditions say independent, so M&M colors are independent, so M&Ms are put into bags, basically randomly and therefore independent, etc. The 10% rule, 122 M&Ms is less than 10% of all M&Ms. Success fail, again I'm taking N times P, N is 122, P is 0.2, which is greater than or equal to 10, and Q is greater than or equal to 10, so we're okay. And then randomization, again, we can assume M&Ms are randomly put into bags and are representative of all M&Ms. Therefore, my conditions are met. I'm going to use the normal model to perform a 1 proportion Z test. Then I'm looking at my hypotheses. Now, we already talked about the null hypothesis is going to be that nothing has changed. So notice I haven't even calculated this yet. I mean, I guess technically I did. Nope, actually I didn't. So I haven't even calculated my P hat yet, which is fine. I don't need to at this point. I just need to know that I'm expecting 20% M&Ms. And then what's my alternative? That's the big question, because a lot of people struggle with coming up with that. And the alternative is based on this sentence right here. It says, does this contradict the company's 20% claim? So contradict doesn't say, does that mean that there's more than 20% M&Ms? Does that mean there's less than 20% M&Ms? It's just saying, is it different than 20%? And so notice the alternative hypothesis I've chosen is not equal to. And then how do I write that in words? Bags of M&Ms do not contain 20% orange M&Ms. So again, it's all based on the fact that it says, does this contradict the company's claim? So don't find this answer up here, the P hat, and say, oh, well, that's less than 20. And so therefore we must be a less than, or it's greater than 20, so it must be greater than. That is not the case. So again, now I'm going to look at the calculations, and here I'm actually doing 2 calculations. I'm performing the test, and then I'm checking it with an interval. And again, all of this is going to be done by hand. So the first thing I want to do is find P hat, which we already said was 21 out of 122, and notice I've calculated that to be 0.172 right here. Now I have to do the test, and remember the test is just my z-score. That's observed minus expected over standard deviation. So my observed is 0.172. My expected was my null hypothesis is that we would have 20% orange M&Ms. And my standard deviation is found using 0.2, not using the standard error, but standard deviation. And I get a z-score of negative 0.773. But keep in mind that my alternative hypothesis was not equal to 0.2. And so a lot of people struggle with, well, that's not an option. When I put this in the StatCrunch to find my value, it's not an option. And here's why. What I did was I found a z-score of negative 0.773. So that's this marking right here on the graph output that I have. So when I'm finding my probability, I'm saying I want the probability that I get a z-score of negative 0.773 or less, which means I'm going to get an observed value of 0.172 or less. Or, because it's not equal to, I'm saying I'm also wanting to figure out this area over here, which would be if I found a z-score of positive 0.773 or more, which would be an observed value of, I don't know, because it doesn't really matter, or more. So I'm saying I want it to be this side or this side, so either side, which means I'm going to find this side, and then I'm just going to take it times 2 because these two sides are the same. So notice that's what I've done here. I'm saying that the probability that p is not equal to 0.2 is the same as 2 times the probability that z is less than that value. And then I found that value using StatCrunch, and then I had to take it times 2 because it was two-tailed. So that's our first one that we've done like this. In terms of my interval, I then have to look at using not standard deviation, so not the same answer that I get here, but my standard error. And I have to remember that if I'm using a 95% interval, what does that mean about z star? So going way back to that video where we talked about critical values, my critical value for a 95% interval, normal interval, is 1.96. And again, you might have to go back to that video if you watched it a long time ago to remember that that's what that number is or how to find it in StatCrunch. So then I'm just saying p hat plus or minus my z star, and then notice here I'm using my p hat value, so that's p hat q hat over n, which is my standard error instead of my standard deviation. And also notice that I've gone to 1, 2, 3 decimal places and not 2. If you round off to 2, you're probably going to lose points on your assessment. When I find, again, this is my margin of error, I get 0.067, and then I take 0.172 minus that value and then plus that value to find my interval. So notice that my observed or my hypothesized value of 20% is between those two values because 0.2 is between 0.105 and 0.239. And with a very high p-value, I would be failing to reject the null because I'm not surprised by this result. So again, let's look at the full conclusion. With a p-value of 0.44, or if you wanted to be very precise, 0.4396, we fail to reject the null hypothesis. We're saying we are not surprised by this. That is a large number. There is insufficient evidence to say that the alternative is true. And again, the alternative is the proportion of orange M&Ms differs from the advertised proportion of 20%. That's what my alternative hypothesis was, that it's different than 20%. I am 95% confident, because I told you to be 95% confident, that the true proportion of orange M&Ms is between, and I've just taken these values and written them as percents, 10.5 and 23.9%. This supports our conclusion to fail to reject the null since the hypothesized value of 20% falls in the interval. And again, we just want to verify that all of that stuff is true, so notice I've just copied and pasted exactly what we came up with on the other page, and I want to do both the test and the interval. So I'm going to go to Stat, Proportion Stats, 1 sample with summary. Remember that p hat was 0.172, but I'm looking at the number of successes, so 21 out of 122. My test, if I want to do my test first, my hypothesized value was 0.2, and again I was looking at not equal to being my alternative, so I compute, and notice I get 0.4416, which is really close to the 0.4396, very close, so that's okay. They're usually not going to match exactly. And then I'm also going to just repeat that proportion stats 1 sample with summary with 21 out of 122 with a confidence interval of 95%, so make sure it matches what I want. Compute, and then again I've got the 0.015, 0.239, so everything matches what I did by hand. So first question says that a statistics professor asked her students whether or not they were registered to vote. In a sample of 50 students, randomly sampled from 700 total, 35 said they were registered to vote. So before I do anything else, let's talk about some of those values. A sample of 50 students means that that is n. My sample size is n. 35 said they were registered. That means p hat is going to be 35 out of 50. Why do they tell me 700? Only so I can check the 10% condition to know that the number of students is less than 10% of the population. So again, I'm finding a 90% confidence interval for the true proportion. Assume the conditions are met. Now, whenever you see this, that means don't check the conditions. Okay? If I say assume the conditions are met, that means I'm not concerned about whether or not you can check conditions. I'm concerned about whether or not you can do the work. State the conclusion in context and then do calculations by hand and then check using technology. So let's go ahead and look at that. Again, not checking conditions, going straight to the answers. I'm using 35 out of 50, which if I wanted to go straight to 0.7, typically that's what I do. I put the 35 out of 50 there for your benefit so you know that's where I'm finding p hat from. I'm using a 90% interval, and that's where this 1.645 came from. So my z star for 90 is 1.645. And again, notice I'm using the standard error, which uses the p hat value of 0.7 and q hat of 0.3 out of 50. So when I do all of that work by hand, I get 0.5934, 0.8066, because we always write our interval from least to greatest. And then I go into StatCrunch, I do stat, proportion stats, one sample with summary. I enter in the 35 out of 50 and make sure I choose a 90% interval because that's what they asked for, and then click compute, and everything else is calculated for me. So notice they're giving me the standard error, which should match up to what I got in here, but it's always best to double check. They're giving me the 0.7, which is my p hat, which I calculated, and then they're giving me my interval, which is 0.5934, 0.8066, basically, which is what I found when I did it by hand. So that makes me feel really good about myself. And then when I write my conclusion, I'm saying I'm 90% confident that between, and then I just write these as percentages, 59.3% and 80.1%, I'm sorry, 80.7% of students are registered to vote. So a couple more questions related to that same situation. First of all, according to a September 2004 Gallup poll, about 73% of 18 to 29-year-olds said they were registered to vote. Does that figure make sense according to what we already found by the professor's students? Well, I just did a 90% interval, and that was like 59 to 81%, and 73 is within that interval of 59 to 81, and so I can say, yes, 73% falls in our interval, and therefore the figure seems reasonable. So now, if the professor only knew the information from the September poll, and wanted to estimate the percentage of her students who were registered to vote within 4%, so plus or minus 4%, whenever you see that plus or minus, you should be thinking, hey, guess what? That's a margin of error of 0.04. And I'm saying with 90% confidence, which means I'm going to be using that margin of error formula, and I'm going to be using my z star for 90%, which should be 1.645. So we did one of these previously, and again, I've just shown you all of the work on this page. But again, I'm just using the margin of error formula, and I'm plugging in what I know. And what I know is z star, which is 1.645, margin of error, which is 0.04, and then I know p hat, q hat, those should be hats, p hat, q hat, which is the 0.73, the 0.27, and then n is what I'm solving for, and then I'm just going to do the algebra. And so I'm not going to go through all of that algebra again with you because I went through that algebra with you in a previous video. dealing with margin of error. So if you need to go back to that, it was the one called margin of error. And I do all of that work and I find n is 333.348. So my conclusion is 334 students. However, that's not awesome because remember I had 700 students and that would violate the 10% condition. So that's not awesome, but that's what they're saying is that's how many I would need to have in order to have a margin of error of 4% with 90% confidence. Okay, let's look at another example. Here we're talking about people programming their televisions. And the goal of Samsung is to have 95% of the people be able to program their TVs. The management produced a new set of directions in hopes that more people would be able to program their TVs. An experiment of 200 randomly selected people showed that 196 were able to program their televisions. Is this strong evidence that the new directions improved upon the 95%? And then check your results with a 90% confidence interval. Boom. That is so much going on, but we're doing this example because this is similar to what you will get on an assessment. You have to do all of it. So first thing I'm going to do is I'm going to check conditions. So notice I didn't go through and highlight or circle or whatever, anything. We'll do that in a little bit. I do want to check my conditions. And again, I'll start by saying independence. Whether or not I can program my TV is independent of whether or not you can program your TV. 10%, we're dealing with 200 customers. Samsung obviously has way more than 2,000 customers, so it's definitely less than 10% of TV users. Random, we're told the study is random. Success fail, again, n times p, n times q, so let's look at where those numbers came from. We are assuming that 95% will be able to program their TVs. We're assuming that nothing has changed, and therefore P will be 95%. So we haven't talked about the alternative hypothesis yet, and we're going to wait a minute to do that. But again, we're looking at 200 randomly selected people, so that's n. That's where I got 200 times 0.95 and 200 times 0.05, and then kind of cutting it close on this one, but they're both greater than or equal to 10. Because all of the conditions are met, we'll use a normal model and a one proportion z-test, and I could say and interval, because really I'm doing both. Now my hypotheses. We know that my null hypothesis is always going to be that nothing has changed. It's status quo. It's exactly how it always has been, which is the 95%. Now, Samsung, or the managers at Samsung, had produced a new set of directions in hopes that more people will be able to program TVs. So we're basically saying more than 95%. So notice that's how I wrote my hypotheses. P is equal to 0.95, which means 95% of people will be able to program their TVs, or it's greater than, so more than 95 will be able to program their TVs. Now let's look at the calculations. The calculations would be, I need to do a test, and the test means z-score, p-value, and then I need to do a 90% interval to verify my results. So my z-score is my observed. My observed is 196 out of 200, or just go straight to 0.98 is just fine by me. A lot of times I'll see students put p hat equals 196 out of 200 equals 0.98 and do that before they get to the z-score, just so we know that we're dealing with 0.98. Notice when I'm using my z-score, my expected value is the 0.95, and the 0.95 occurs also down here when I'm doing my standard deviation, which is the 0.95 times 0.05 over 200. I do all of that work and I get 1.947. Then this is where I would pop over to StatCrunch to find the p-value, and that's what this is called, is the p-value. And again, the way that I write that notation, I'm saying the probability that p is greater than 0.95, which was what my alternative hypothesis was, by the way, is equal to the probability that z is greater than 1.947, and then all of this was done in StatCrunch. And then I'm going to also find my interval that's 90%. So before I do that, keep in mind this is less than 5%, so I should be rejecting the null. in favor of the alternative hypothesis. But let's check it with the 90% interval. The 90% interval, again, is centered at p hat. It always is centered at p hat. We don't use p at all in the standard or the confidence interval. This 1.645 is because a z star for 90% interval is 1.645. And then again, I'm using 0.98 again because that's what I have here. And then 0.02, which was 1 minus 0.98. I do all of those calculations together, and then I get my confidence interval. And then, not a bad idea to also let StatCrunch do all of the work, and notice StatCrunch verified my p-value, verified my confidence interval, lower limit, upper limit, match with what I found by hand. What's my conclusion? Well, the p-value is low. It's much lower than 5%. So if I don't tell you an alpha, assume 5%. So I'm going to reject the null. There's sufficient evidence that more than 95% of people are able to program their TVs. Again, that's just the alternative hypothesis. We're 90% confident that between 96.37 and 99.63% of people will be able to program their televisions, and notice that my hypothesized value of 95 is out here, and so therefore that supports rejecting our null since 95 is not in our interval. One more to try, and again, if you haven't already tested yourself by trying one of these questions before I go through it, I strongly encourage you to do that. So this would be a good time to press pause. Otherwise, let's go ahead and look at this one together again. So this one says 30% of wells that are drilled find adequate water. A man claims he knows how to find water by using a special forked stick at a higher rate than 30%, so he thinks his special forked stick will help him to find water better than the average person. You are suspicious of him and check with 80% of his customers to find that 27 of them have wells he found with adequate water on his first drill. What do you conclude about the man's claim? So is he full of it or not? Check your results with a 90% interval. So again, first thing, check the conditions. Independent, whether or not we found adequate water is independent. 10%, assuming the man has more than 800 customers. We don't know that for sure, but that would be 80 times 10. So we need at least 800 customers for that to be less than 10%. Random isn't given, but we can assume that 80 are representative of his customers. Success fail, n times p, and again, let's talk about what p is. If 30% of wells that are drilled find adequate water, we expect that the man who, with his special forked stick, is still going to just find it at 30%. That's going to be my p. So that's where p came from here. And of course, q, 1 minus 0.3. And then n is 80 because that's how many customers we surveyed. Both of those are greater than 10, so the conditions are met. We'll use a normal model, one proportion, z-test, and interval. My hypotheses, the first hypothesis, the null, is always that nothing has changed. So its p is 0.3. My alternative is based on the context of the question, and the context said that this guy thinks he can find it at a higher rate than the 30%. So notice that is my alternative hypothesis, that the man will find water more than 30% of the time. Now to do my calculations, again keeping in mind that the null was that p was equal to 0.3 and the alternative was that p was greater than 0.3. My calculations, again, will be my test and my interval. My test uses my observed value, my p hat, of 27 divided by 80, which is 0.3375. Notice here I'm going out to 4 places because I want to be precise. My expected value is what I expect to have happen, which is a hypothesized value of 0.3. And then notice this is the standard deviation, PQ over N square root. I get a z-score of 0.7324 because this alternative was greater than. I'm finding the area to the right, the greater than. Again, I'm saying the probability that P is greater than 0.3, which is the alternative, is the same as the probability that z is greater than the z-score that I computed, which gives me 0.2321. Again, that value is pretty high. I'm comparing it to 5%. That's more than 5%. That's 23%. So I should be failing to reject the null. But let's verify with our interval. Again, observed value, p hat. Notice the 0.3 doesn't come into play at all. So I'm taking my observed value. I'm again taking that p and that q based on the p to find my calculation of my interval of 0.2505 to 0.4245. Again, I had already said I should be failing to reject the null, but the hypothesized value of 0.3 certainly is between these two numbers, and therefore again I should be failing to reject the null. Use StatCrunch to verify your results. Notice my p-value matches my p-value, my interval matches my interval, and if it doesn't, go back and check your work. My conclusion, the p-value is quite high, so I fail to reject the null. There's insufficient evidence to suggest that the proportion of wells the man finds higher than the 30% we would otherwise expect. We are 95% confident that between 25.1 and 42.5% of all wells that are drilled will find adequate water, which supports our conclusion that things haven't changed, because 30 is in the interval.